Next speaker, Ethan Klein, are you present?
Yes, sir.
Nice background.
Thank you very much.
Okay, I can see them and I heard, yep, great. So our next speaker is Ethan Klein. He's a student at MIT, second-year student, working with Eric Danagulian. Going to talk to us today about neutron resonance analysis using a DT generator. So Ethan, please go ahead.
Thank you very much. It's great to be talking with you guys today. I know I wasn't able to be in person back in March, and it seems that way again, but nice to be chatting and providing an update. Unfortunately, I have not been back in the lab since then, so the results you'll see today are primarily simulation work, but of course we'll have experimental work expected in the fall. So the topic is a common one in terms of my work for this consortium, and we'll be discussing use of neutron resonances using a DT neutron generator, so essentially a compact system for analysis of fissile material. So in terms of motivation, one of the initial reasons that we were pursuing this work is in terms of nuclear warhead verification. So for potential future arms control treaties, ideally you would have true material identification and isotopic composition analysis. As of today, there is use of some non-intrusive inspection equipment, mainly in terms of passive detection of radiation. Ideally, our goal would be to work towards an active detection mechanism. Another motivation is the fact that X-ray imaging and most passive detection techniques, such as those currently used, are not suitable for true isotopic analysis of mid and high Z materials that will be found in those kinds of nuclear warheads. And our reasoning behind looking in the epithermal neutron range is the fact that it's already been proven for a variety of other applications, has been studied for several decades, and then certain improvements in terms of compact neutron generators make it a worthwhile pursuit at this point in time. So with regard to mission relevance, as I mentioned, epithermal neutron resonance imaging has been used before for imaging fresh and spent nuclear fuel. I show the results there from one paper from Los Alamos recently published, where you can see the results of resonance imaging, so viewing on tungsten resonances there, which allow you to see impurities within those fuel rods, fuel pellets, and then below I show a diagram from previous work out of our group, again regarding use in a physically cryptographic warhead verification method. So these are the kinds of applications that NNSA works with that we would like to be able to develop a more portable system for such analysis. So in terms of background, speaking to neutron resonances, on the left here, I just have a simplified diagram showing a neutron incident on a target nucleus, forming a compound nucleus. You see there's the different quantized states. If the excitation or energy of that incident neutron matches one of those states in the compound nucleus, you see an increased likelihood of interaction. And then that can be seen on the right here in terms of these characteristic attenuation dips in transmission spectra. For this plot on the right that I'm showing, that comes just from just calculated NDEF values, neutron cross-section values, neutron transmission, for a mock-up of a warhead as proposed by Feder back in 1990. And so just to clarify, this is showing neutron transmission based on calculated cross-section values just for a uranium pit along with a tungsten tamper. So we would not be proposing this use for essentially analysis of the full warhead mock-up, but rather following removal of the explosive material. So why is it that we're really interested in the epithermal regime? So one reason is that there are key isotopic signatures for special nuclear material. So U-235, 238, and Pu-239 and 240, as you can see on the right, all have kind of these isotopic fingerprinting in terms of their neutron cross-sections in this range. Furthermore, there are no resonances for common shielding materials. So it is a nice place where if there is any shielding from lead or from plastics, essentially there's no energy dependent phenomena. And so what you'd expect is that any kind of energy dependence in your neutron transmission spectra will be a result of the mid-high Z materials, which we're looking to analyze. And thirdly, again, many of these neutron resonances in this region are N-gamma, resonances. And so you do see additionally secondary interactions that could be detected, such as an off-axis gamma detector, which is something that we're exploring, which could give you additional information in terms of doing the isotopic fingerprinting of the target material. So in terms of our technical work plan, again, it seems we're still stuck in the stage of Geon 4 simulations to optimize our experimental setup and to determine true feasibility of this method. Before I had left campus, we had done some initial laboratory setup of a simplified apparatus using a DT generator that we currently have already in our lab vault. And ideally, we would then use that for validating our experimental results. Following verification in our own lab setting, we would like to test different fissile materials at a national laboratory, ideally using a DT generator that has shorter neutron pulse and neutron pulse time and a larger neutron flux than what we currently have. And then again, we would like to make improvements to the actual detection requirements. So in terms of our experimental setup, here's just a quick little mock-up. So essentially we have our DT generator that's within a vault. We have the pulse generator outside of the vault. So we produce a neutron within the DT tube. The idea is to pre-moderate it in beryllium, which I'll speak to in a minute, which allows you an end-to-end reaction to increase your epithermal neutron flux, moderation in a high-density polyethylene moderator. Some of those neutrons will then be transmitted on into the target, and then in this case, a HEU pit, and then carry on into our detector setup, which consists of an enriched in lithium-6 GS20 glass, as well as a cadmium foil just in front of that to remove essentially any thermal neutrons, any wraparound neutrons from room return. The signal was read out in channel 1. Channel 0 is tied into the start time of the DT pulse generator. So between those two channels, the time difference allows us to reconstruct the neutron's energy and thereby create that energy spectrum of neutron transmission. And so again, the focus of this talk will mainly be on the actual epithermal neutron production. So as I show on this slide, this is the spectrum essentially for that moderation assembly that I showed on the previous slide. So this is for the DT neutrons in the forward direction through 5 centimeters of beryllium and then 3 centimeters of high density polyethylene. On the right here, I show you just in dark gray, the part of the spectrum that we're utilizing. And then in the inset here is the actual flux density, just normalized to the width of those EV bins. And as you can see, it's a pretty spatially kind of distributed system. So this assumes a 2.5 centimeter diameter DT target. I'm not sure honestly what it is for our system and lab. And in terms of the actual moderation, so I mentioned before, one modification we've made to our previous setup was to move to using beryllium for the end-to-end reaction. Some things that we've seen here are essentially that it's actually reduced the moderation time within the moderator assembly compared to a solely plastic moderator, which is beneficial because it reduces that time uncertainty and hence uncertainty in neutron energy. So our system is still currently limited by the DT neutron generation pulse, which for our system is at 10 microseconds. Many currently can be within 3 to 5 microseconds, which is much improved. And as you can see here for our moderator assembly, the uncertainty and moderation time is generally sub microsecond in terms of a full width half max. And again, it improves towards higher energies, but unfortunately, both our detector resolution drops there as well as your inherent time of flight resolution on neutron energy. So these are kind of some of the key results of our current simulations running with the beryllium pre-moderator. So essentially what we show is we can produce a high quality neutron beam with good gamma neutron discrimination, which was previously a problem. So acceptable epithermal neutron detection efficiency. So essentially the two key changes that we want to make based on our simulation results were again, one, the use of the beryllium pre-moderator, and then two, essentially cutting the thickness of our lithium glass detector to improve our gamma neutron discrimination. And what we see is that if we go from a 1-inch thick neutron scintillator down to a 5 millimeter thickness, one, we can cut that piece, improve the solid angle coverage. And then in addition, we only decrease our neutron detection efficiency down to about 50%, while severely cutting out detection of gammas. So what you see in this plot here just shows the epithermal neutrons energy during the epithermal time of flight window. In blue, I show those particles that are detected. In red are those that are not detected. So you see that we do see gammas produced in end capture and other events in the neutron pulse in its interaction in the environment, but very, very few of those gammas will actually be detected, and furthermore with sufficient energy deposition that they could be mistaken for a neutron in pulse height analysis. And again, we still have pretty good epithermal neutron detection efficiency, even for the thinner GS20 scintillator. Some key parameters here I show on the right. Our epithermal neutron flux is up to about 4 neutrons per centimeter squared per second. For us, that's good. Obviously, it's not as good as using it, say at a laboratory large-scale facility, but that's pretty much the best that we've achieved based on our simulations for a compact setup using a DT generator. Furthermore, the average accuracy in the energy is on the order of 0.2 eV, so that's within the width of resonances in this region. And again, like I mentioned, 50% neutron detection efficiency. So this is actually a significant improvement over the plastic-only moderator. Here are just some additional figures just to demonstrate that, again, the vast majority of these neutrons on the x-axis, I have their time of flight energy reconstruction, y-axis is their true energy. And so that we see that the vast majority of them are within 15% error, which is pretty good. On the left here, I show a spectrum where the ideal is the true neutron energy. And this is a plot of neutron transmission. In blue, it includes any gammas that were detected, and it uses the reconstructed neutron time of flight from the Geant 4 simulation. So you can see that we do have pretty good neutron energy reconstruction. And as I showed on the previous slide, we're also increasing our actual neutron flux at the detector. So those were two of the key goals that we were hoping to do by optimizing our setup using the Geant 4 simulations. So we count it as a success. Very quickly, this is just kind of thrown together, but preliminary results. So on the left here, I show you a calculation for transmission through a HEU pit just based on the NDEF values. And so what you can see are the neutron resonances leading to these attenuation dips. Here around 3 eV, around 6 eV, and then around 8 eV. And then here on the right is the transmitted neutron flux that we're seeing in our Geant 4 simulations from the, again, reconstructed time of flight energy. And you see those same kinds of resonances starting to appear. I will say that the simulation run is only for a couple seconds of measurement time. So we are pretty pleased that as we continue, to really bring that up to maybe 5 or 20-minute measurement times, we really should be able to see those resonances. And I should say that all these simulations assume the 5 microsecond neutron pulse width. So with that to conclude, I'd just like to say we're very pleased with the simulation results of adding the beryllium as a pre-moderator to our moderator assembly. We really do believe that using a 5 millimeter thick neutron detector compared to the 1 inch will give us a much improvement. And lastly, I never thought I would miss working in a windowless underground vault, but having been out of lab for several months now, I am eager to return, and hopefully the next time I get a brief, you guys will actually have some experimental results. So with that, here are some next steps. But really, I'd just like to say MTV has been amazing for my development so far. I participated in the recent MCNP Polemi workshop. I have a virtual internship scheduled with Lawrence Livermore for the summer to look at some faster DT neutron generator setups that they have. And we're also exploring potential further collaboration, both at Livermore and PNNL. So we're really pleased with how everything's going. And with that, I'd like to acknowledge both the team at MIT and NSA for my fellowship, as well as for their funding and for the consortium. So thank you very much for your attention.
Thanks, Ethan. Very nice talk. If you have questions, please put them in the chat. I don't see any there yet, so I will start with a question. I'm curious how well the cross-section data, neutron cross-section data in the epithermal range is actually known. If you look at the NDEF libraries, if you looked at the variances in those data, and can you speak about that?
Absolutely. Yeah, personally, I don't think it's as well known as clearly as it is in the thermal and fast regime. The same applies actually for the neutron capture gamma spectra. Generally, that's known for thermal neutrons. So that's something that, again, we would have to further explore. So that will be somewhat tricky in terms of actually benchmarking. But again, when we hope to get actually into lab and to actually use just some how to say, some kind of calibration samples. So we have like thin plates of tungsten and of other mid to high Z materials. So ideally, we would be able to calibrate on some of those just single isotope transmission experiments.
Great. Sarah Polte's asking, which materials do you have available in your laboratory? Obviously, once you can get back in for testing, DU, HEU, other stuff, what do you guys have available?
Yeah, we definitely have DU available. I don't know if we have any HEU available. That would be some of the hopes, again, from collaborating with some of the national laboratories. But we definitely do have DU available. We've been using tungsten and I believe silver as, again, kind of calibration sources just to see where the resonances show up for us. But yeah, that's all kind of subject to when we're back and when we'll be testing. But that, again, that's another reason that we would really like to collaborate with some of the national labs to have kind of greater access to some of the resources they have that we just don't have on campus.
Yeah. So you mentioned silver. Does it have, I mean, I guess you would be looking for materials that have similar type resonances, both in energy and also in the spread, right? So does silver qualify?
It does. I know in the past we've used silver, tungsten, and molybdenum as well. Those are kind of some of the three key proxies for either uranium or we could do plutonium, but really that kind of gets into tricky issues because of the neutrons that are being generated in the rest. And I think this is more seen for some of the uranium type design kind of work.
Yeah. Did you mention how thick the beryllium is? And did you optimize that?
Yeah, yes. Optimized by simulation, not optimized in person, obviously. But yes, for 5 centimeter thick beryllium and then 3 centimeters thick of the poly. And so essentially that was something that we saw that I think that the 3 centimeter thick poly is sufficient to moderate some of the neutrons produced in the inelastic beryllium production, but not too thick that you start to, again, kind of thermalize too many of your epithermal neutrons. And also increase that moderation time. But it seems, at least to starters, 5 centimeters seems to be the right thickness of beryllium.
That makes sense. Because it seems like you lose a lot. This is a standard 10 to the 8 generator.
That's the assumption for all that.
Yeah. I mean, you're ending up with few neutrons per centimeter squared downstream. Yeah.
Correct, and that's at a 1.5 meter time of flight distance, which should be just on the verge, kind of ability to resolve the resonances of, again, what we understand to be the widths in the epithermal region. Yeah,
that's the trick, right? You need just long enough to get that resolution, but not kill your flux, right?
Exactly. Previously, we did 2 meters. It seems 1.5 would be as close as we could get, and probably with our 10 microsecond width, we'd have to move back to 2 meters.
Yeah, that makes sense. I look forward to seeing you back in the lab.
Yes, sir.
Question from Dick Lanza. What is the attenuation of explosive in a warhead, or is this measurement assuming a bare pit? Also, how does the thickness of the actual pit affect your observed rates?
Oh, yeah, exponentially. And in terms of the explosive, I mean, that is something that, looking at it, it would just totally kill us, not to mention the kind of moderation and any capture gammas that you're going to have in that explosive. So I think this would really have to be for one stage beyond, again, not the full mock-up of the warhead, but if we're talking about dismantlement, it could be at a stage once the explosives are removed to verify the nuclear nature of the pit.
Great. I'll do a last call for a question in the from the audience if anyone has a question. If not, thanks, Ethan. Appreciate your time and your excellent talk.